in state 2 and a different Gaussian in state 3. The idea is that for any given output, you can talk about the likelihood or the probability of given that output given that you were in a particular state. And then the last thing you need is that initial distribution pi, right, that says what's the probability of starting at a particular state. This is about the time when you might say, what does this have to do with computer vision?
What does this have to do with vision?
I'm so glad you asked. All right. Well, another way of phrasing what we've been doing is, given some sequence of observations, which model was most likely to have generated those? So using our previous clothing and weather example, so suppose you're seeing some sequence of clothing, right? So you check the clothing that people are wearing each day, and you see this coat, whatever. And then the question you want to ask is this Philadelphia, Boston, or Newark? The idea is that presumably what you've been doing is you've been collecting sequences of these observations from Philadelphia, a bunch of them from Boston, a bunch of them from Newark. You have trained a model, and we'll talk about that later. You've created a model that will tend to generate sequences like you see in Philadelphia or in Boston or Newark with the same statistics that they have. And then given some new observation sequence, you'd like to say, which one is this? Now, notice that if we were checking Boston versus Arizona, you basically wouldn't need the sequence. It doesn't rain in Arizona for the most part. And you could say, well, do I see umbrellas? Okay. And since it's always lousy weather in Boston, I live there. If you see bathing suits, you know it's actually Cape Cod. So the idea is, just from the individual elements themselves, you could determine whether it was Boston or Arizona. The whole idea of representing the time series is that there's something about the sequentiality that matters. It's the statistics of one thing following another that is indicative of the actual class. And what you're doing is you're building some models of those time series so that you can then, given some observation sequence, you can say which one's most likely. And what we're going to do is we're going to apply that to computer vision. All right, welcome back. I hope you took a nice break there. As you can see, I'm totally, actually it's another decade. I just kind of look the same. So what we've done is we've laid out sort of the general idea of a Markov process, Markov system, and also a hidden Markov model. And what I want to do now is talk about sort of 3 computational problems of hidden Markov models, and then we'll talk just about a simple application of this to computer vision. Also, just as a word of note, I am not going to go into the detail of different parts of lots of the math, just one part of it, and then the rest I'll, as they say, leave it to the reader or the viewer as an exercise to go get schooled up in it. Because the details were less important than knowing that it could be done, and then it was applied to computer vision. All right, so we have a hidden Markov model, and we said that our hidden Markov model is lambda is a triplet of A, B, and pi, where A is the transition probability, B are the emission probabilities, and pi was just the distribution of where things started. Well, given that a HMM, given a machine, there are 3 computational problems we can look at. And the first one is this. Basically, given some observation sequence, okay, so remember, O1 through O cap T are the observed outputs from 1 to cap T. So that's a particular sequence. You could ask, what is the probability P of O given that machine? That is, what's the likelihood that that machine generating that particular sequence? And this is really the classification recognition it says problem, but actually how you use it for that, right? Assume I've got a couple different HMMs, maybe 3 of them, and they each represent an activity, and let's assume that the prior of which activity is going on are equal. All right. So then if I have the priors are equal, all I care about is the likelihood of the data given the model. And the HMM would allow me to evaluate the likelihood of the observed sequence for each of the given models. Whichever one was highest, that would be the one I picked. That's a generative model like we talked about before. So the evaluation problem is, substance, the key problem at runtime. It's one we'll actually talk about. Another problem is what's called decoding the sequence. So remember, you have a sequence of observations, and the question is, what's the single most likely sequence of states to have generated that sequence of observations? So it's not all possible ways these observations could generate. It's just the single most likely sequence, sometimes called the decoding problem. And Sometimes you care about that, sometimes you don't. When you do, it basically has to do with saying, well, if the states have some particular meaning to me, right? Remember we talked about sunny, rainy, cloudy, so they might have some specific meaning. I might want to say, okay, here's what I think the underlying state sequence is. Actually, sometimes in genome work, et cetera, they actually want to know what the underlying state sequence would be. But if you're actually just doing it for recognition, then that's some sense less important. And then the third problem is in some sense the most complicated problem, and that is, okay, I give you a bunch of training examples, a bunch of these O sequences, train a model, learn the lambda that, and the way you learn it is you pick the one that maximizes the likelihood of getting that observation. It's a maximum likelihood method. It's actually called EM, expectation maximization, and we'll talk about that just a little bit. We won't actually do the math of that part. So let's take a look at problem one. That is, what's the probability of getting the observation sequence given lambda, given an HMM? And so first I want to look at a naive solution, and then you'll see how the cool solution is so much better than the naive solution. So let's start off by pretending, assume for the moment we actually know the sequence of states. Okay? So that's Q sub 1 through Q sub cap T. Right, Q sub 1 through Q sub cap T. That's the actual state at time 1 through time cap T. Each one of them is an S sub J, right? So maybe it goes from state 3 to 2 to 4, whatever. 1 through T is the time, okay? So we're going to assume that. The other thing we're going to assume is that the observations only depend upon the state that you're in. So when we say independent observations, what we mean is that if you knew the state, then the probability of observation is just dependent on the state and not dependent upon anything else. Well, if that's the case, then the probability of the particular observation sequence given the state sequence, well, because of independence, it's just the probability multiplied times each other of the output of the particular symbol seen at time t, given that you're in the particular state at time t, and that taking the whole product, and that's just these B variables, right? So B of Q1 of O1 means the probability, given that I'm in Q1, whatever Q1 happens to be, of outputting O1, and et cetera. Okay? So if we knew the state sequence, then we could just multiply this to get the observation of the likelihood of the observation sequence given the state sequence. But for any given state sequence, I can tell you the probability of getting that state sequence. Right? It's just a very simple product shown here, right? So if I know it's Q1 through Q cap T, then it's the probability, here's pi of Q1, of starting in that state. And then A of Q1, Q2 is the probability of going from that state Q1 to whatever the next state Q2 is, times A, Q2, Q3, all the way up to A, QT minus 1 to QT. All right? So assuming I knew the sequence, I could tell you the probability. Well, you say, in that case, I can do the following. Given that I can compute the probability of a sequence, of an observation sequence given a state sequence, and given that I can compute the probability of any given state sequence, well then obviously we can compute the probability of getting that output sequence by just summing over all the different state sequences, right? Taking the probability of the state sequence times the probability of the observation given the state sequence, summed, as I said, over all the state sequences. Okay? You could just do that. Of course, the problem with doing that is it would take you a long time. How long? A really, really, really long time. And the reason is, this is summed over all possible paths, all possible state sequences. All right? Well, if there are n states and there are t time steps, that's n to the t. Okay, exponential in time, n to the t, and each one costs t calculations because I have to figure out the probability of O. So the complexity of that is t times n to the t. That, as we say, is a really long time. So it's not such a good solution. So you think we can do something better? Well, of course we could, or I wouldn't be standing here wasting your time. Here's the efficient solution. The trick is that we're going to use recursion, and I'm not going to show you something called the trellis diagram, which is a way of thinking about a graph model of this, but what we're going to take advantage of Remember the Markovian property? The Markovian property says that the probability of going to some state only depends upon where I am now. It does not depend upon how I got here, right? So if today is sunny, the probability of tomorrow being sunny is not affected by whether yesterday was rainy, snowy, or sunny. That's my assumption. It's my first order Markovian assumption. So to take advantage of that, we're going to define some auxiliary variables and define a recursive algorithm. So the first thing we're going to define is what's called the forward variable alpha, okay? And alpha sub t of I is defined to be the probability of seeing all the observations up until time t and at time t being in state I. Okay, that's exactly what it says in this book. Well, now there's a box inside the box there. So it's the probability of seeing everything from 1 until t and being in time t being in state I. The really cool thing about that is I can define a recursive definition for this very easily, all right? So you start off, A1 of I is what? Well, it's the probability of having seen the observation at time 1 and the probability of being in state I at time 1. Okay, well, that's easy. Pi sub I is the probability of starting in state I, and Bi of O1 is the probability of seeing that first symbol if you were in state I. So that's how you initialize it. Now comes the really cool thing. And before we write it out, think about it this way. At some time t, the probability of landing in state j is going to be, well, either I was in state 1 before and I ended up at state j, or I was in 2 before, or I was in 3 before, or I was in 4 before, right? And these are what are referred to as mutually exclusive. So the probability is just the sum of them. And that's how this is written here, right? What this says is that alpha of t plus 1 of j, so that's the probability at time t plus 1 of being in state j and having seen all the 1 to t plus 1 observations is just, well, just as I said before, it's the sum over all the different possible states, right? There's n possible states of possibly being in those states at time t. That's what alpha t is, right? And alpha t also includes all of the observations up through t, times the transition probability of going from I to j. Remember, we're trying to compute alpha t plus 1 of j, going from I to j. So that's the probability that I land in the state j. And now I also have to talk about the output symbol at time t plus 1. Well, that's b sub j of ot plus 1. All right, and there's no way of thinking that I can reach that j state from any of the preceding states, so I just define that recursively. That means I can do one more really cool thing, okay? So I could obviously run this all the way to t. So I could tell you the probability of seeing all of the observations, 1 through cap t, and landing in state 1. And all the observations and landing in state 2. And landing is... Suppose all I want is the probability of the observations. Right? I don't actually care what state I end up in. Well, that means that the probability of the observation given the machine, and that's what we're trying to compute, is just the sum of all the alpha cap t of i's, right? Alpha cap t is the probability of seeing all of the sequence of I, meaning and landing in state I. I sum that up over all the i's, and that's the probability of the entire observation sequence. So you recursively solve that problem. So remember before it was n to the t, which is a really, really awful number. The complexity of this is just n squared t, okay, through the recursion. Each time step you have n squared things you have to look at. You do it t times, and so it's n squared t. And for any reasonable numbers, n squared t is way, 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 way less than n to the t. All right. So that's that efficient solution of the forward, using the forward algorithm, and allows us to solve that first problem. The main point of what I just showed you is that instead of looking at all possible paths, by using recursion, we can look at n squared t paths. And remember, the reason we can do this recursion is that recursive formula only looks back at the previous state. We're taking advantage of that Markovian property. And with just the forward algorithm, we could evaluate the probability of seeing that entire observation sequence given the machine. So, for example, and I haven't yet told you how to do this, if we had trained up a bunch of HMMs